Hey everybody. So we're back at it and looking at some more energy problems here in terms of dynamics, energy and systems. So we're gonna talk about springs. All right. We're gonna talk about energy stored, released in springs, and looking basically at Hooke's law again, revisiting Hooke's law. We learned that last year. Linear restorative forces. Everything's going to happen in waves again. Remember our wonderful waves unit? You guys made instruments. We talked about all kinds of things wave-like. Well, anytime we have one of these things that behave like a spring, we end up with a wave. And what do I mean by behave like a spring? The idea of behaving like a spring really means that it obeys Hooke's law. And Hooke's law states that a restorative force, so whenever I move something out of an equilibrium position, the force that wants to pull it back to its equilibrium position is directly proportional to the amount of extension or compression of the spring in the opposite direction. So here's my spring. It has a length L, and I'm going to extend it by X. So this full length is L plus X, right? So then, because I've extended in this direction here, I'm having an opposite force wanting it pulling back into its equilibrium position. We have an equilibrium position, it wants to get back to equilibrium. In the same way, if I compress it, the force is in the opposite direction. It pushes it the other way. Okay, so Hooke's law allows us to quantify this restoration force, this ability to go back to an equilibrium position. All right, so we've learned this already. This is Hooke's law, that the force, the restorative force measured in newtons, is proportional. That's not correct. That's newtons per meter. Okay, sorry. So the spring constant is newtons per meter, and that allows us to make a proportionality, right? Because we know that the force is proportional to x, right? But it's in the opposite direction. To make it from just a proportionality to an equal thing, we need one of those wonderful constants, right? If I graphed x and f, and then the slope of here would be k, right? And I'm using vectors here, so I use the negative sign to show that it's in the opposite direction. What about energy? How much energy is stored in a spring? Energy measured in joules. So we know that from the work energy theorem that the energy is going to be equal to the work done. And remember that work, what's the definition of work? Work is equal to, oh, that's bouncing, F delta D. Let me just move that back a little bit so it doesn't bounce as much. There we go. Right, the work is equal to F, the force multiplied by the displacement. Right, so I know my force is equal to kx. So on my graph, I can make a linear representation of force, and the work is going to have to be all this stuff underneath, this area underneath this curve. Right? When we multiply the extension times the force, we're talking about the area under this curve. So all you fancy pants calculus people, the other way you can express work is equal to the integral of the force multiplied by dx. So the infinitesimal piece here, dx, and then I have the function as a f here, let's say force as a function of x, dx, from, let's say, my original point to, let's say, point x prime that represents the full extension. Right? That's the calculus way of doing this. And if this was in vectors, we can do vector calculus to make this a vector, and we multiply this by the dot product of the displacement vector. Okay, and then yeah, so that's another way we can look at this. All right, so but let's not worry about it. Let's just think about this is the area under this graph, under this kx curve. Okay, so how's that going to work for us? We know that this is a triangle, right? The area of this thing is going to be base times height. So the force applied times the displacement times a half, because it's a triangle, and we know the force applied is kx, so we end up with this lovely expression that the energy stored in a spring is a half kx squared. So as I double the extension in the spring, I quadruple the energy. Notice this is very similar to our half mv squared idea from kinetic energy, right? So it looks sort of the same, but it's based on slightly different principles. Okay, a lot different principles. Well, okay, so this is a way that we can define elastic energy. Okay, what does this mean to the actual motion of the spring and how much energy we have? So let's say I have a spring. I have a mass on a spring, and it's attached to a fixed wall here. This is fixed. This can't move. And I can move it either in the negative direction, and it goes to a maximum extension of A, so negative A, or in the positive direction, the opposite, A. So if I pull this out, here, I'm at point A. I've extended this to point A. At that point, it's going to have no velocity. That's its farthest extension. It's going to accelerate out to that point, and it's going to stop once it's reached that maximum extension. At that point, it'll have gained the highest amount of potential energy. It's stored all that energy into that into the spring. Right away after that, it's going to start converting it into kinetic energy in the opposite direction. Okay, but at this point, at point A, this an elastic energy, let's call it E, is going to be also my total energy because it's going to be stopped, right? And then once it also has the highest force because it's the highest extension. The force is going to be equal to negative Ka. So there's going to be a force acting in this direction, pulling it back. Right? So it's going to start accelerating back towards the equilibrium point, but thanks to Newton's first law, it's going to still have inertia. It's going to overshoot. It's going to get to point 0, right? And it's going to have the largest velocity because it's going to have the lowest potential energy, but the highest velocity, which means it's going to have the largest K, right? That potential energy is going to be equal to that elastic energy at the point A. Right? All that elastic energy is converted into kinetic energy. Oh, that got hideous. Wow, erase. Okay, all that elastic energy is going to be converted into kinetic energy. There's no potential energy at that point, and there's also no force. So it's not being accelerated either left or right, but it's moving still. So because it has this velocity, remember it has inertia. Okay, it has inertia. So it's going to keep going, and it's going to keep going to point A, well, negative A, because all that kinetic energy is then going to be transformed into potential energy again. This is the same, this potential energy is going to be the same elastic potential energy at A. So we had energy at A, converted it to kinetic energy, then stored it again at A minus, then we're going to convert it to kinetic energy again, and it's going to go back and forth forever. Well, we know that's not true. There's going to be damping, so it's going to have to slow down eventually, right? So it's going to do some wobbles, but it's going to have some sort of exponential envelope where it's going to wobble down. Okay? This is some e to the negative kx function as an envelope that sort of slows it down. This is damping. Right? But we don't have the math to deal with damping, so let's not worry about that. It's just another term in our differential equation that we have to solve. But we're not at differential equations yet. We're only in grade 12. Thank goodness. All right. So what this does, again, we've seen this last year, right? That a linear restorative force leads to a sinusoidal solution, right? So we have a period. Over the period, it starts off at... What the heck is going on here? That's a funky... That's the period. Why are these things moved? All right, something happened. That's not correct. Okay, this is t over 4. This is t over 2. Where is it? This is 3/4 t, and this would be t. So, pardon me, something happened with stretching, and things got discombobulated. All right. So we end up with a sinusoidal solution for this is x as a function of t. Right, this function here is x as a function of t, and it ends up being sinusoidal. Okay, why is it sinusoidal? We can use heuristic reasoning by looking at, it has inertia. So here we extended it out to A. It gained kinetic energy, it lost all its elastic energy, but it had inertia, so it kept going. But why this shape? Why not like a zigzag? We did this a little bit last year. I'm going to go quickly over it, but we end up with the solution looking like this, right? So we have, you can ignore this side, but let's say it's just sine. There's a period, this guy here, this is the, what we call these omega naught, the natural frequency of the harmonic motion. This is the frequency that it wants to vibrate at. If I let it go, that's the frequency it wants to vibrate at, which is related to the spring constant divided by its mass. The stiffer the spring, the harder the spring is to move, the faster the thing will vibrate. The more mass there is, the slower it'll vibrate. Okay, and it's a square root of that. If you want to see why this is the case, this has to do with, right, so we want to get this from, we know that the force, right, is equal to negative kx. And we also know that force is equal to mass multiplied by acceleration, Newton's second law. Now, if this is just quickly, guys, I'm going to go into calculus. And anybody who doesn't want to go to watch calculus, just ignore, skip. The beauty of these videos, just skip ahead. Skip ahead. Don't worry about it. Okay, this is just a proof of why the sign shows up. Okay, and so again, just ignore it. All right. Now let's just rearrange here. That acceleration is equal to minus k over mx. All right, so the acceleration is proportional to the position, but I know that acceleration is the second derivative of the position. Right? So the second derivative of x, let's call it now, let's call this x of t. Let's call this x of t. Right? So now I have this thing. This is called the differential equation. This is saying that there's some function x of t that when I take the derivative of it twice, spits out the original function plus multiplying by this negative k over m thing. So what is a function that if I take the derivative of it gives me the same function back but negative? Anyone in calculus will tell you that that's a sine function. So the derivative of, let's do this quickly, derivative of sine x is equal to cos x, which means that the second derivative of sine x will be equal to the derivative of cos x, which is negative sine x. So this function then, right away, you can see that sine satisfies this expression. But the problem is there's this negative kx over m. So this doesn't exactly work. We need a function now that, let's try d by dx squared sine of, let's just do k over m. What's going to happen there? I'm going to get the derivative. Let's make it first derivative first. Okay. If I take the derivative of sine k over mx, I'm going to get, let's write this down. Over here, I'm going to get a cosine function, k over mx, multiplied by k over m, using the chain rule. So I'd have to do the derivative of sine, but then I have to take the derivative of the inside of the argument, of the cosine, of the sine argument, sorry. And the derivative of k over mx is just going to be k over m. So then if I take the second derivative, I'm going to end up with this happening twice. That's going to be negative k squared over m sine k over m x. Right? So if I take the second derivative of sine k over mx, I end up with this negative k squared over m squared. But I don't want that. I just want k over m. So we're going to have to do it for, let's erase all this. It's all going to work out nicely if I take if I have my stretching factor or whatever of my sine and cosines, it works for cosine as well. Spoiler alert. Will have to be a square root. Goodbye, all that. Let's do the same thing. So we're going to take the derivative with x of sine root k over m square root k over m x, right? That'll give us root k over m cosine. Where's the eraser? I gotta find that eraser. There we go. Cosine root k over mx. And then if I take the second derivative of that, so doing it again, I'll have to have that root k over m come out twice, squaring that, so that's just k over m. And this time it's going to be negative sine root k over mx. And look at that. So we have the same function here as here, but the only difference is we multiplied by negative k over m. So that will become a solution. So therefore, one of my solutions is going to be sine, and the other one is going to have to be a cosine. So therefore, one of my solutions here, I can write this down, x as a function of t is going to have to be equal to sine root k over mx, right? However, if I multiply any of these functions by a constant, it won't change the function, right? The constant will come out. So I have to say that there's going to be some constant in there. And if the argument has some sort of constant added to it, that's not going to change what my derivative does, right? Because in the chain rule, when I take the derivative, it's still going to give me the derivative of the argument here is still going to be just root k over m. So I still have to add this plus c. And this is also the case for, this also works, so I have to write the same thing for cosine. Because cosine is another function that adds to the thing. And really, I have to add, whoopsies, go back. Sorry, then I also should add another constant, let's call it d, to the whole system, so that I am, that would be the general solution of that differential equation, right? So what we saw here. Now, don't worry too much if all that calculus lost you again. Just know that if we have a linear restorative force, the solution has to be sinusoidal. Okay, so that works for a spring, right? So we end up with this idea here, that when I extend the spring, it keeps bouncing back and forth along these sinusoids. So there's the sinusoid representing the position, and then there's the sinusoid representing the velocity, and there's the sinusoid representing the acceleration. As you can see, the derivatives, there's slopes. So the slope here, right, that's 1, which is here, or some constant. And here at the top, the slope is 0. Tangent of the curve is 0. It's 0. This is negative. Slope is negative here. We have a negative value here. Slope is 0. Tangent is positive. We have a positive value. The same thing over here. But notice the x function and the a function are the exact same, but flipped. They're negative. So the second derivative of position of this graph, of this x position graph, gives us the acceleration graph because of the properties of sine and cosine as functions. Okay, that's really how the sine functions work. That the derivative of sine is cosine, and the second derivative of sine is negative sine. Okay? And it all has to go back to F equals ma, right? The acceleration is equal to k over m multiplied by the position. Well, negative k over m, right? Because it has to be negative there, right? So linear restorative forces produce sinusoidal motion. Waves. Anytime we have something like that, we have a wave. It could be. So what are some examples here? So let's look at a pendulum. Pendulum, we know, wobbles back and forth as a sinusoid. And why does it do that? Because it has gravity acting on it. It has gravity and tension. Right? There's a string stopping it. That ball wants to fall. If I push it outside of its equilibrium position, gravity wants to bring it back to that equilibrium position because there is a component of the gravity here in the, let's put a theta here. There is a component of the gravity in that theta direction. There's a component of gravity radially outwards that will be opposed by the tension in the string. Right? But there's also going to be this piece that's going to want to pull it back. Very similarly, on the other side, we're going to have the same situation that's going to want to pull it back. Right? So we know that F equals ma. But in this case, my mass is going to be equal to, my force is going to be equal to mg multiplied by sine of my angle, because this angle here is going to be the same angle. Right? We did this last year a little bit looking at pendulums. So we're going to end up with this idea. We can cancel the m's. So my acceleration is going to be equal to g sine theta. All right. So is this an example again of a simple harmonic motion? It's got a sign there. It doesn't have an x. It doesn't look like Hooke's law yet. So let's adjust this a little bit. Let's add here. Let's make a triangle. Let's call this L, the length of my string. Let's call this X, how far I've extended it, my amplitude. Okay. So then sine theta will also be equal to G. Opposite the theta is X. My hypotenuse is L. So, or another way I can write this is that my acceleration is going to be equal to G over L in the X direction. Now, you may notice that this X and the direction here are a little bit funky. This is a simplification. This doesn't work exactly. It has to do with the torque. There's actually a torque acting on this. This angle changes. I can't explicitly do this. I'm cheating here a little bit because we're only in grade 12 and we don't have all the calculus and all the physics to understand this. Really, there's a torque. Torque is equal to the force times the radial arm, right? Torque is actually a cross product of R and F, and then we have to worry about moments of inertia and weirdness. But I can, at this point, grade 12, we're okay. We can do a little bit of a cheat here and use this triangle here. It doesn't exactly work, but I can get to this point and again say that my second derivative of position, or the rate of change of position, is in this case negative. Let's go negative g over Lx. Where did I come up with this magical negative? Where did that negative come from? How did a negative just magically appear? Anyone see why? Because it's always opposing the direction of sorry, what word am I thinking of here? Opposing the direction in which we extend it, right? We moved this away from its equilibrium position and it wants to go back. So it's a linear restorative force. And you can see here we're going to end up with, again, just like a spring, we're going to have a function, let's get x of t, that's going to be equal to sine of, in this case, it'll be the square root of g over L multiplied by x. Okay, and that gives us this is our natural frequency. This is our omega naught, the natural frequency that the pendulum wants to spring. And just like we did in the pendulum lab in grade 11, it depends on the length of the string. It doesn't depend on the mass, right? Our masses cancel here. It doesn't depend on the amplitude that we oscillate at. It only depends on the length of the string. Actually, it's the frequency, right, is dependent on 1 over root L, which is one of the things we did in our pendulum lab last year. Okay? And hopefully you guys remember that. But again, we're back to this same idea that a linear restorative force leads to I'll put the negative to cheat. That leads to a sinusoidal motion. Okay? Another one, guitar string. A guitar string is the same idea. There's a string at equilibrium, and I can stretch it out of equilibrium. I can hit it here. This is where it's being plucked here. So this is at hugely extended scale, right? I'm not going to pull a string that far away when I pluck it, but I'm going to have to extend it, and it's going to want to go back. And again, this restorative force is proportional to displacement. It has to do with the string itself is extended to a longer distance, right? This is the equilibrium length of the string, and then I've extended it by some distance. Let's call it delta x. So it behaves like a Hooke's spring, and we end up with having sinusoidal oscillations, and we end up with music, right? And then we have these overtones happen. Because I hit it here, not in the middle, I'm going to have multiple overtones. I'm going to have my regular fundamental harmonic, then my first harmonic, then my second harmonic, and all these things happening, and we end up with music, and we like it, all right? It's pleasant to our ears. This case, though, the frequency is related to the omega is equal to tau over mu square root. Okay, tau is the tension on the string, and mu is the linear density, how much mass per centimeter in our spring. Okay, which gives us, again, sinusoidal oscillations, music. Right? Because music or sound, what you're hearing me with, what's going into a microphone that's coming into speakers into your ears, is just oscillations in the air, compressions and rarefactions of this air moving back and forth, back and forth, back and forth, back and forth. Okay? Oh, now let's go even weirder. Okay? A diatomic molecule. This thing, let's call this oxygen here. So O and O, right? That's just oxygen. It behaves from a quantum mechanical point of view like it has a spring in between them. Okay? I can come up with a potential energy of this thing. It looks something like this, and it'll oscillate. And this part here, this potential energy, will look kind of parabolic. It's called the Leonard-Jones potential. And in this area, this region where it's closely confined, wow, that's loud. Oh, excuse me, that was my wife's cell phone. That was loud. All right. So again, this is a Leonard-Jones potential. Don't worry about all this. Is just Mr. Stone. And what is that? That's a Charmander. There's a Charmander's foot sticking up in the background. Thanks, kids. Anyways, so because this potential behaves like a quadratic, it ends up behaving like a Hooke's law. Hooke's law, remember, that has an elastic potential energy 1/2 kx squared. This is the same idea, so it's going to end up these oxygen molecules are going to want to bounce back and forth and back and forth. Okay, and they have some sort of natural frequency that they vibrate at. Okay, and we can measure this. We can actually see this. This ends up being microwave length light can excite these things like this. So this is how your microwave works. Okay. It is much more complicated by quantum mechanics, but for now we don't have to worry about this. This is a linear restorative force between two atoms. Okay, so in a molecule, it doesn't have to be diatomic; it can be multi-atomic. These bonds behave like springs, and they can have multiple modes. Just like a guitar string can have those overtones, there's multiple modes, especially because it's in 3 dimensions. Here, let's go to some fun here. Okay, so let's look at some wobbly molecules. Carbon tetrafluoride. Let's check out carbon tetrafluoride. If it loads. Come on, you can do it. You load, there we go. All right, check out all these modes of oscillation. This is carbon tetrafluoride, and their molecules wobbling back and forth, behaving like little springs that have natural frequencies. These are different types of bending and stretching vibrational modes that we can see at certain frequencies. This is a weird way of measuring frequency. Chemists like to measure frequency as centimeter -1. Okay, and I'll let you guys think about that. Remember the wave equation? Remember the wave equation? Why does centimeters minus 1 work as a... Remember that... this pen doesn't work on this. But remember that the speed of light is equal to the frequency times the wavelength. How would centimeters minus 1 work as a unit of frequency? I'll let you think about that. Let's go back here. Let's check out another one. I'm on the screen. Let's look at it. Let's look at a fun one. Water. Look at all the wobbly boys. Look at them go. Whoop, whoop, whoop. They're dancing away. Look at these fundamental modes of vibration of water molecules at different lights. Okay? All right, let's try another one. Let's look at sulfur hexafluoride. What's that going to do? Let's say load. Look at all these wobbly dudes. All these different modes of... Look at this guy. Okay? Look at that. All right? So as you can see, there's multiple ways in which things can oscillate. Okay? Let's go back. Where are we going? So atomic bonds can behave like springs, and atoms can behave like sinusoidal oscillators, simple harmonic oscillators, right? So an atomic bond can lead to simple harmonic motion. Hi, Claire. Give me a second, guys. Sorry about that. A little bit of interruption from my kids. Remember, I have 4 kids, and they're all at home. Things are kind of crazy, but oh well. Where are we? Yes, atomic bonds behave like nice springs. Oh, here's a fun one. Okay, so let's say I take the Earth, and I somehow magically drill a hole through the Earth, and then here's me, and I jump into the hole. What would happen? What happens if you jump into that hole? Remember that the force of gravity, right, is equal to, what's the force of gravity equal to? G M M over R squared. Yeah, that's the force of gravity relative to this distance R, right? So how is that going to affect my motion? What's going to happen to me? Am I going to fly out the other side? Am I going to bounce back? What would happen to me if I somehow managed to do this? Have some sort of spacesuit that allows me to do this. Okay, I want you guys to think about that, and we'll talk about that later. Okay, you can go in the Discord and answer on there if you'd like, or send me an email or something like that. But here, this is this question: what would happen if I jumped into that hole? Gedunken experiment, thought experiment. A Gedunken experiment is a thought experiment. It's an experiment that doesn't really make sense, but you can do it in your brain, right? So, reply an email on a Discord or something like that. Okay, and then you guys can work on those practice problems. All right. Okay, so I hope you're all doing well. I hope everything's okay with you. Things are crazy. I heard some of you got put into D2L courses, which, from what I've heard in the board, these are just sort of shells. I wouldn't worry about them at the moment. They're just putting something together in the background, and you guys weren't supposed to get those emails, so don't worry about it. Keep doing what we're doing. Send me questions. I haven't got any questions. I haven't heard back from a lot of you. I hope you guys are doing okay. Okay. Just send me, if I haven't heard from you, just fire me a little message on the Discord just to make sure you guys are okay. All right. Stay safe. Stay home. Do physics. All right. See ya.